So our next speaker is Pedro Moreno-Sanchez. He's an assistant professor at IMDEA, and he's going to talk about security, privacy, interoperability in payment channels, payment channel hubs.
Okay, so as Lefteris mentioned, today I'm here to talk about security, privacy, and interoperability in payment channel hubs. My name is Pedro Moreno-Sanchez, and I'm currently working on as assistant professor in the Institute software. As I claim, I'm looking for interested students interested in the topics of blockchain. So if you're interested in the topic I'm presenting today or anything related, feel free to reach me afterwards. So today I'm going to talk about the scalability problem. And I'm pretty sure that you have heard this already. So basically the idea is that we have this decentralized data structure that we call the ledger that records every single transaction that happens in the system. And I want to say that this is actually good. It provides public verifiability, which means that we can really verify the correctness of every single transaction that happened in the system. The downside of that is that we require a global consensus or permissionless consensus in the case of Bitcoin, where everybody checks the whole blockchain and effectively in practice limits the transaction rate to something like 10 transactions per second. And this, of course, in practice is not good enough, and we should go to something like the level of Visa or other centralized payment system, which allow us around 10,000 transactions per second, and we can gather a growing number of users and transactions. As in the topic of this workshop is scalability, I think that the main approaches for scalability can be grouped in two main trends. One is called on-chain, and the main idea here is to design new ways to perform consensus. And the main approach, as we have seen, is sharding. On the other hand, we have what we call off-chain solutions. And the idea is to keep blockchain and the consensus algorithm as it is, but use it as little as possible. Use it only for disputes among participants. One example of this approach is payment channels, which is the one I'm interested in focusing in this talk. And we have some examples in practice, like the Lightning Network. And there are many other projects that are being developed, and some of them are already even in mainnet, like Bolt, Perum, Liquidity Network, Commit, and so on. So as I mentioned, I'm going to give you an alternative way to handle scalability, which is the off-chain solutions based on payment channels. I'm sure that most of you have heard of the concept of payment channel before, but to make sure that we are on the same page, let me give you a bit of background. So imagine that we have a setting where we have two users, Alice and Bob, and Alice has some coins and she wants to buy the book about distributed systems from Bob. One possible way is that Alice perform a single transaction for every time that she buys a book. But this, of course, will require a single transaction every time, which is not really good for scalability. Instead, what she can do is create an open channel, or she can open a channel with Bob, let's say for 5 coins. In order to do that, she has to create a Bitcoin transaction where she spends 5 coins from her own account to what is called a multi-sig contract, or simply a Bitcoin account that is shared between Alice and Bob and can be spent further only when both of them agree. When such a transaction is signed, can go into the ledger, and the channel is effectively open from Alice to Bob. Now, Alice can use this channel to pay as many times as she wants for Bob. Imagine that the book costs 1 Bitcoin. It's a really expensive book. So Alice can use the channel to pay for it as follows. So she creates now a transaction where she spends the 5 coins in the channel and distributes in the following manner. She gets 4 coins for herself and 1 coin to Bob, and she assigns herself this transaction. Now, Bob, when Bob sees this transaction, he knows is correct, and the only thing left to make it valid is to sign it himself. And he knows that he can always do that because he has his own signing key. But instead of putting it in the blockchain, he will just keep it local in his memory, and because effectively it counts as a payment. When time passes and Alice wants to buy another book, let's say, then Alice can perform a payment exactly as before. She can redistribute the amount in the channel, giving 3 coins to herself and 2 coins to Bob. And as before, she will sign this transaction and give it to Bob. And as you can imagine, you can perform this process several times. And at the end, when Bob wants to retrieve the money from the channel, he will sign the last date and put this date on the blockchain. So basically, intuitively, what payment channels give you is that with only two transactions on chain, one to open and one to close the channel, allows two users to perform arbitrary number of payments off chain. This is nice, but the problem is that it allows only payments between two participants. What we would like to have is to have payments between any two users in the system. The strawman approach would be that every user or Alice will open a single payment channel with everybody else in the network. However, this is not feasible in practice because Alice will have to lock coins to each of the channels, and Alice might not be that rich. So one of the solutions in practice is to exploit what is called gateway channels or hubs. The idea is that every user opens a payment channel, single payment channel with the hub, and use it as an intermediary to perform transitive payments between themselves. Imagine, for example, in this setting where every user has opened a payment channel already with the hub, that Alice wants to send one Bitcoin to Karen. In order to do that, Alice will send one Bitcoin to the hub, which eventually will forward this to Caro itself. And in that manner, Alice will have paid to Caro in a transitive manner. Also, to economically incentivize the hub to actually perform this forwarding of the payment, Alice will not pay exactly one Bitcoin, but also one Bitcoin plus a bit of fee in order to incentivize the hub and pay for this forwarding service itself. This is the setting that we are interested in this work that I'm going to present now. It's called Anonymous Atomic Locks for Scalability and Interoperability in Payment Channel Hubs. And this is a work that has been mostly done by Erkan Tahiri and also under supervision with myself and my colleague Matteo Maffei, both in TU Vienna. Let me tell you first what we mean by security in such a setting in Payment Channel Hub. So if we look back in the setting of the transitive payment between Alice and Carlos through the hub, what we mean by security is that this payment should happen atomically, meaning that Alice will pay the hub if and only if the hub forwards the payment to Karen. Otherwise, hub will be able to steal money from Alice itself. From the privacy point of view, we consider a setting where the hub is the malicious guy and wants to figure out which of the senders on the left wants to pay to which of the receivers in the right. In a bit more formal way, we want to make sure that whatever payment protocol we design for the payment channel hub, the intermediary, is not able to distinguish between two cases. One case where blue Alice pays to blue Carol and green Alice pays to green Carol, and the other case where they pay in the other way around. So blue Alice pays to the green Carol and the green Alice pays to the blue Carol. Finally, the third property that we are interested in is interoperability. And basically what we mean by that is to create a payment protocol for payment channel hubs that is compatible with Bitcoin and as many cryptocurrencies as possible. And to make sure that this payment protocol is compatible with Bitcoin and cryptocurrencies, we want to make sure that we don't change the scripting language that they have. We use the functionality that they provide today. What we have observed over our work is that this is not an easy task. There are several approaches out there for performing payment channel hubs. Have, for example, Peru or Liquidity Network, but they heavily rely on the Ethereum-based scripting language. There's also Vault, but this approach for payment channel hub requires opcodes that are not available in Bitcoin. There's also other approaches that implement a payment channel hub but require an additional trust assumption, that require the use of trusted execution environment. And this additional trust assumption may not be suitable for several blockchain applications. Also, there is a protocol called blind swaps that only relies on cryptography, in particular requires Schnorr signatures, but they are not available in many cryptocurrencies, and in particular is not available in Bitcoin yet. Perhaps the solution that is closer to ours is Tumblebit, which is fully compatible with the current Bitcoin and relies on a smart contract that you might have heard of before. It's called hashtag block contract. However, this is only available in Bitcoin and is not possible in cryptocurrencies that don't have a scripting language. Let's say, for example, Monero or Mimir. And apart from that, as we will see later, the efficiency of this protocol can be further improved, and we have done that with A12. But before giving you the details of our protocol, I wanted to go a bit into details of a building block. It's called adapter signatures, because we have seen it is really useful not only for payment channel hubs, but also for other payment applications and blockchain applications. So the idea of adapter signature is the following. So we have the typical setting, two users, Alice and Bob, and they have their own pair of public and secret key. And now, apart from that, they share the following information. So they have a payment channel, as we have seen before, that is in the contract with two public keys, one belonging to Alice and one belonging to Bob. Also, there is a transaction that sends coins from the channel to Bob. And apart from that, they have the knowledge of what is called the adapter. An adapter is a third fresh public key pair, public key and secret key pair. And out of this adapter, both of them know only the public key part. The secret key is not known to them yet. And in this setting, what we want to do is a protocol that achieves the following two goals. So what we want is a protocol that allows Alice to create a half signature or her share of the signature over the transaction TXA, such that Bob can finish it only if Bob gets to know the secret part of the adapter, in this case, secret key C. Also, the second property that we want is that if Bob ever manages to learn SKC and finish the signature and eventually get the coins from the transaction A, Alice should also learn the secret part of the adapter. Let me tell you a bit in details how this construction for adapter signatures will work in the case of Schnorr signatures. It's a bit simpler than with ECDSA. So we are exactly in the same setting as before. And now the first thing that they do is that they generate shared randomness, as they will do with the normal two-party Schnorr signatures. Now the trick that we need to use for embedding the adapter into the signature process is that when they compute the joint randomness of the signature, they not only use their own shares of the randomness, in this case G to the RA and G to the RB, but they also include the public part of the adapter. And intuitively, without going into too many technical details, we do that because this forces whoever is going to create the signature to actually embed the secret key part of the adapter itself in the signature, as we will see later. Once they have done that, they compute the challenge part of the adapter of the Schnorr signature, as is shown here. And finally, they share to each other the half signature, the share of the Schnorr signature. So Bob will give his share SB to Alice, and Alice will give her share SA to Bob. There are 2 points interesting to look at here. First, even by combining these two shares, they cannot create a valid signature yet because they don't know the secret key C. And for the security point of view, it's important that they can actually verify that these shares are correct up to knowing the secret part of the adapter. At this point, and depending on the application that we are using adapter signatures, Bob will get to know the secret part of the adapter, SKC. And when he does that, he can actually compute the final signature by adding his own share, the one of Alice, and the secret SKC. And with that, we have achieved the first goal that I have mentioned in the previous slide. The second goal, Alice can extract the secret key C out of the signature because she knew already the 2 shares out of the signature from before. So the only thing that it has to do is take the complete signature and extract the SKC with a simple formula. As I mentioned, I have shown to you the construction of Schnorr in the paper. We have on our paper, we also have the construction over ECDSA and also the ring signature as used in Moreno. I will put to you the pointers in a future slide. If you didn't get all the details of the cryptographic construction for adapter signature, it doesn't matter. So I'm gonna step one step back, and I'm gonna use a graphical representation of adapter signatures in the remaining of the talk. In particular, whenever I'm using adapter signature, I'm gonna depict it with this figure where there is a first step where Alice inputs the transaction and her signing key. Bob inputs his signing key, and he gets his half of the signature, the share of Alice. And this part, I will call it the lock part of the adapter signature. Later, when Bob gets to know the secret part of the adapter, then I will depict it as here. So he will input the secret key to the protocol, and Bob will get to learn the final signature over the whole transaction. And Alice will get not only the signature, but also the secret part of the adapter. And I will call this the release part. So with adapter signature already in our background, we can give a first attempt to build the A2L protocol. The setting is as before. Alice has a payment channel with the hub. The hub has a payment channel with Bob, and both of them have the adapter PKC. And at this point, nobody knows the secret part so far, only the hub. For that, our protocol will build on 2 instances of the adapter signature. And in the first one, the adapter will lock coins in this transaction H that goes from the channel to Bob. Bob, at this point, after the lock has happened, cannot finish it because he doesn't know the secret key C at this point. Instead, he will ask Alice for help to pay or to buy the secret key C out of the hub. In order to do that, Alice will lock coins to the hub. And because the hub knows the secret key C of the adapter, he will use it to release the lock and to get the final signature. But out of the property of the 2-party adapter signature, Alice will get to know the secret key C from the hub, which then can tell Bob, and Bob would eventually release the coins that were initially locked by the hub itself. You have to believe me here, but we can prove that this Stroman approach is actually secure, meaning that Alice pays the hub only if the hub pays to Bob. The problem comes with privacy. If you take a closer look, you can see that both of the channels are using the same public key adapter, and also the hub is using exactly the same secret key for both instances of the adapter signature. In that manner, the hub can easily and trivially actually link who is paying to whom. We go to our notion of privacy, and we have the setting that we had before. The hub will see that there are 2 users, in this case, Blue Alice paying to Blue Carol using exactly the same adapter, and another instance of a payment where the Green Alice is paying to the Green Carol, which is using exactly the same instance of the adapter, in this case, PK prime. So the hub can easily see who is paying to whom, and therefore privacy is actually not achieved. So in A2L, in our protocol, we refined this Stroman approach to overcome this privacy issue that I just mentioned. Particularly, we have the same setting as before, where the hub has a channel with Bob with a public key C as the adapter. But apart from that, Alice and Bob will introduce their own randomness. You can think of it as their own secret key through the process. And with that, we have the same message pattern as before. So the hub will lock coins to Bob, but also the hub will include the encryption of the secret key C, of the secret key of the adapter. And the encryption is done with the public key of himself. So Bob gets to learn the encryption, but he cannot extract the SKC yet at this point. So as before, as in the Stroman approach, Bob will ask for help to Alice. But in this case, he will do 2 actions before that. The first one, he will ask Alice to adapt the adapter. Sorry for the redundancy, but he will take his own adapter, PKC, and adapt it using the randomness from both Alice and Bob. Says that intuitively, the 2 adapters in the 2 payments are now indistinguishable or not linkable for the hub. Second step, Bob needs to make the secret key of the adapter consistent with the changes that he did to the public part. So using the homomorphic operations of the encryption, Bob will include the randomness from both, from Bob and Alice, in the encryption itself. And now, with these 2 pieces of information, Alice can lock coins to the hub, as before, and also include this new version of the encryption. With that, the hub will learn the encryption, can decrypt, learn the randomized version of the secret key C, and run the release part of the adapter signature at the Alice part. See that once Alice learned the secret part randomized, the secret key C, she can de-randomize it with her own randomness, and also Bob can do it as well. So he will actually get to learn the original SKC, the one that he needed to unlock or release the coins that originally were locked by the hub. Again, for the same reasoning as the Strawman approach, this A2L is secure. And from the privacy point of view, the intuition is that now the adapter in the two payments, the one from Alice to the hub, and the one from the hub to Bob, are not linkable anymore because the one is the randomization of the other. And again, because also the secret keys are also randomization of each other. Very quickly, we have implemented a prototype of this A2L. We have evaluated the computation and communication overhead in a LAN network. And we were interested in comparing our protocol with Tumbleweed, as I mentioned, probably the closer to our solution. What we observed is that we have about 3 times faster computation overhead, and we reduce the communication overhead with a factor of about 33%, 33 times. I think the interesting point here is that this reduction is not only from tricks in the implementation itself, but then we actually reduce the number of operations and communication overhead asymptotically. And without going into many technical details, the issue is that in Tumbleweed, they use a technique, use cut and choose, and this requires that messages have a number of elements that are linear in the security parameter. And in A2L, as you have seen, every message has a constant number of elements. So this heavily reduces the communication overhead in our protocol. We also have advantages in terms of interoperability. In fact, what we have seen is that the key aspect for us in interoperability is the implementation of adapter signatures. So in this paper, in one, we have formalized this notion. And here we have given the construction based on Schnorr and ECDSA. And as I mentioned, we also have a construction based on the print signature of Monero. And basically, if we want to adapt an A2L to any other cryptocurrency or any other system, for example, we want to have post-quantum payment channel hubs, what we need is to create a post-quantum version of the adapter signature, which we are now currently working on. It could be also possible that Alice pays the hub in a certain currency, let's say Monero, and hub pays to the Bob in another currency, let's say Bitcoin. And if they use different curves, we will need to make sure that public keys and secret keys are consistent among different curves. But there are efficiency knowledge proofs that can be used for that matter. And of course, when you implement this, there are other practical challenges. So if you use different currencies, they have different exchange rates. So you have to make sure that they don't lose money from the different exchange rate of the different currencies. And also every cryptocurrency has a different block creation rate. So you have to make sure that the locks and the release part of the adapter signatures are synchronized correctly. So this concludes my talk. So in this talk, I have given you an idea of A2L, an overview of our protocol, which is a cryptographic protocol for payments and payment channel hubs, where we focus on achieving security, privacy, and interoperability between different cryptocurrencies. As in the paper, if you're interested, we formally prove the guarantees of security and privacy. As I mentioned, A2L has several advantages in practice. So it's compatible with Bitcoin, and even when Bitcoin adopts Schnorr, A2L could also be used on top of it. But it's also possible to deploy with cryptocurrencies that don't give a scripted language, like Monero or Mimblewimble. As I mentioned, A2L is more efficient than a Tumbleweed, and at the moment, the most efficient Bitcoin-compatible payment channel hub. For that reason, there are some blockchain implementation in practice, like the Coinbit network, that are already testing and creating proof of concept of A2L. For more information, the paper is available in this link. We also have a prototype implementation available there, and we are looking forward for your comments, your questions, and feel free to ask me now and reach us after the talk as well. Thank you very much.
I have a question on the interoperability. First of all, what are the assumptions if I want to make payments between two cryptocurrencies using a XML channel networks? What should I trust? And if you can describe how it would work, it would be really cool.
Yes. So basically, as any other payment channel construction, you have to trust that the consensus underlying each of the blockchains is correct. So you have a correct consensus. And then from the application point of view, when you have different coins, for privacy, we require that every payment has the same amount. And basically, the idea is if you have different amounts, then the hub can easily link who is paying to whom just looking at the payment amount itself. So in practice, we will need a way to make sure that every payment has the same amount according to the exchange rate. Imagine, for example, I want to pay to you 2 Monero, and the hub forwards the corresponding amount in Bitcoin, but this amount will be different every time. So we need to adapt that according to the exchange rate.
So the hub sets the exchange rate, basically.
That would be one approach. The second approach will be that you use the concept of Oracle or some other party that you trust only for the exchange rate, but not for the actual payment. So in practice, we can think of different approaches to do
that. Thank you very much for your talk. It's really nice to have also a layer to think. Thanks.
Yeah, thank you for the invitation, Lefteris.